I think we should start our session now. Good news is that we have 100% of presenters which are available here. So it means that 1.5 hours we have 15 minutes per single presentation, including discussion, assuming that we would like to take part in a bus trip. Yeah. So please try to respect the time limit. My name is Krzysztof Okarma. I came from Szczecin, northwest Poland. It's my great pleasure and honor to chair this session. I would like to invite the first presenter, Mr. Miroslav Stanek from Czech Republic, who will present a paper entitled Psychological Stress Detection in Speech using Return to Opening Face Ratios in Glottis. Please, the floor is yours.
Thank you. Well, dear audience, please welcome to my presentation. My name is Miroslav Stanek. I'm with the Department of Radio Electronics at the Faculty of Electrical Engineering at Brno University of Technology, and I would like to present to you our paper oriented on speech signal processing, exactly named Psychological Stress Detection in Speech using Return to Opening Face Ratio in Glottis. So, speech processing as well as estimation, then I'll be talking about return to opening face ratio, description, and of course I will show some experimental results. Well, the speech signal processing was performed on our created database containing recorded fluent speech under the normal moods and under real psychological stress for 24 different Czech native male speakers. We can divide this database into two main parts. The first part contains six speakers. For these speakers were recorded separately spoken Czech vowels with long duration. These separately spoken vowels are further used as the training sequence and training data for further experiments. From these separately spoken vowels were selected some appropriate sectors from the beginning and from the center parts. Well, for the glottal estimation, we used two well-known algorithms: the direct inverse filtration and the iterative and adaptive inverse filtering. So, for receiving the training data, we used the separately spoken Czech vowels of the length, duration, and this figure shows that the glottal shapes of glottal pulses don't vary on the duration of spoken vowels. This is the same part of the Czech word, and this word was spoken shortly, and this word was spoken longly. As we can see, it's more or less the same, identical. Well, each individual glottal pulse is then further processed separately. It is normalized in amplitude and in the time domain for receiving the most uniform results. As we can see, there is no difference between the shortly spoken phoneme and for the longly spoken phoneme. Each individual pulse is divided by its peak into two main parts, the opening and the return phase. Yeah, and in our experiments, each phase is divided by the first percent step into observed sectors. That means the 20 observed intervals are used in our experiments. The zero level of each phase is exactly in the position of the pulse maximum. Yeah, and for each phase and for each interval, the three different parameters are calculated: the kurtosis, skewness, and the area. As you can see, we used return to opening phase ratio, so it means these parameters calculated for the return part are further divided by the relevant values received for the opening part, defined as by this equation. This table shows an example of the 5% interval selected sector at the vowel's beginning, varying for all Czech vowels, varying on the actual state of speakers. Well, our experimental results were performed on the second database part. From the fluent speech were found the vowel segments, and these vowel segments are further processed. Optionally they are normalized in amplitude domain for receiving the possible impact of the sound normalization on the psychological stress recognition, and further from these waveforms, the glottal pulses are estimated by the chosen method, and these pulses are further processed. They are normalized and filtered for removing some parasitic pulses. We used in our methods, in our experiments, eight different methods. These methods are varying on the selected algorithm for glottal pulse estimation, the direct inverse filtration, iterative and adaptive inverse filtration, applied on the vowel's beginning for training data, or on the vowel center for the training data, and or on the normalized sound or not. Yes, and in our experiments was performed on 6 different classifiers for reaching the most suitability for precise psychological stress detection. As we can see, this is the table of received results due to the total number of selected methods, of observed intervals, and of used classifiers. We received 960 different efficiency results. As we can see, the best results was received for support vector machine classifier applied on the 5% interval, for the iterative and adaptive inverse filtering applied on vowel's beginning and normalized sound, this approaching approximately 96% of the success psychological stress recognition. Further, the Gaussian mixture models were received efficiency approaching the 95%. This figure illustrates the impact of the sound normalization. If that means if we use the same method as the method 3, and we will before the glottal pulses estimation, we will normalize the sound in its amplitude domain. We will receive the more stable recognition results, as we can see on the black line. Yep. And finally, we are at the end of my presentation. So I would like to conclude it. The psychological stress using the RTOs can be successfully recognized by using the iterative and adaptive inverse filtering estimation, as well as the sound normalization applied on the beginning. Sorry for the mistakes. At the beginning of vowels for receive the training data of our classifiers, and the most appropriate classifier for that topic is the Gaussian mixture models. And over the all classifiers, the biggest differences between the normal and the stressed speech is at the range of 50 to 80% selected interval. So, due to the further performed experiments, this method seems to be phoneme independent, and as well as language independent. So, this method can be further expanded and applied for testing the other actual emotional states of speakers, or alcohol intoxication, and so on. So, thank you for your attention, and wish you a nice day in Palanga.
Thank you. So, are there any questions from the audience?
Yeah.
Yes.
How many recordings were used? And you also mentioned that it's language independent.
Yeah.
How do you know that?
We tried this method at on the SUSAS database. Do you know SUSAS database? Stress speech under that's English. That's records pilots. Yeah, and we received more than satisfied results. About 86% of recognition, the stress recognition. So, due to this reason, we expect it will be language independent. We would like to apply these methods on other emotional databases like MODB for the Deutsch or something like that. And our recordings, we record the 24 different speakers. Yeah, for each speaker, we have the two different records under the normal mood and under psychological stress, and each record is approximately 30 seconds only.
Are there any further questions? Maybe I will have one or two. Do you have any initial results related to female speech from the data sets or not?
No.
Not yet?
not yet, because we recorded the real stress on our students before the final defense of their thesis, and on our department the female students.
Okay. Yeah. And the second question, very short. Have you considered the principal component analysis for the classification?
No, not yet.
Okay. So, are there Any further questions? No? So thank you once again. And I will invite the second speaker, Mr. Olev Zelenik from Slovenia. The paper written by two researchers from Austria and Slovenia entitled Multi-Resolution Feature Extraction Algorithm in Emotional Speech Recognition. So quite similar field of interest. Please present your results.
So hello everybody, my name is Olev Zelenik. Today I will present a paper entitled Multi-Resolution Feature Extraction Algorithm in Emotional Speech Recognition. For an introduction, we will look at the concept of emotions and how emotional speech recordings can be obtained. That will be followed by explaining the differences between the parameters and the actual emotional speech features. Next, we will carry on with the presentation of the development of theoretical procedures, which will focus on the concept of multi-resolution, where the use of multi-resolution windows gain a better time frequency utilization of values for each feature. At the end, we'll present some comparisons on the recognition rates between the single resolution and the multi-resolution approach. So research in the field of emotions is one of the most confusing and still open research areas. By rough estimation, there are more than 90 different technical definitions for emotions were created in the last 20th century. Slight variations in facial expressions, voice, posture soon received different notions for emotions, which resulted in a long list of different emotions. So Ekman was the first to define the 6 primary emotions that became known as the Big 6 or basic emotions. These emotions are joy, sadness, fear, surprise, anger, and disgust. And they are generally very well accepted between scientists because they do not contain any mixtures of other emotions. To carry out experiments, emotional recordings have to be obtained. There are 3 ways to get emotional recordings. So the first is spontaneous, which are gathered from real situations. The second option is acted emotions, which are usually provided by professional actors in the recording studio. And the third one are the induced emotions, where we try to get the natural responses from people in a controlled environment. For our work, we have chosen an emotional speech database that is a part of project interface, because in addition to the recordings in English, French, and Spanish language, we also have recordings in Slovenian language. And the emotions used here are the Ekman's Big 6 emotions. So automatic emotion recognition systems rely on the quality of the chosen features extracted from segments of speech signal of different size. The width of these segments, also called processing windows, determines the 2 types of features. When features are calculated using narrow windows that span between 20 and 100 milliseconds, they are called short-term segmental features. To calculate using narrow windows, to then cover the whole recording, these small segments are shifted, and the parameters are calculated each time until the recording is fully covered. Long-term features are calculated on the longer-term intervals, usually like words, phrases, sentences, even vowels. And we can also use the entire recording to calculate them. From a speech recording, a lot of parameters can be calculated. But what distinguishes those values from the emotional features is that for emotional features, we need values that are depending on the emotion used, and they also have to be independent from the recording duration and from the speaker, from his sex and from his age. An example of a good feature is a difference in fundamental frequency between the angry and the neutral speech, when especially in angry speech we see big differences in the parameter values, while in neutral speech this is more, we don't see those big differences. Emotional speech recognition was carried out using short-term features, where the focus was on the gathering of information only for selected segments, while consciously excluding information that is based on the duration of individual elements of speech, like duration of vocals, pauses, speech rate, and etc. In order to achieve, especially in order to achieve lower computational complexity and higher robustness of recognition. To see the operation, we will look at the recording of number 10, which sounds in my language the set, by a male speaker with a duration of 950 milliseconds. The whole recording is divided into overlapping windows with the window height of 64 milliseconds and the shift of 16 milliseconds. Because of this, the whole duration is incremented to 3650 milliseconds. With the addition of voice activity detector, non-speech segments are removed, which can be seen in the second picture, so that we are left with approximately 65% of the recording. The majority of emotion recognition studies use features that rely on extracting information from lower frequencies, which seldom extend above 1.5 kilohertz. With that in mind, we propose a very strict removal of features that, in order to preserve only the most relevant segments of speech where lower frequency bands prevail in the speech signal. The algorithm that provided the best results compares the amount of energy of lower frequencies to the amount of energy of higher frequencies. If the energy is significantly higher in the lower frequencies, then the frame is kept, like we see in the second picture. Otherwise, it is discarded, which can be seen in the third picture. Discarded frames must be analyzed that no useful information is discarded. So as it can be seen in the third picture, no useful information is discarded in this case. With this algorithm, only 30% of the material is retained. And everything else was discarded because that only produces noise in the results. From all windows, features are calculated and their values are further processed. First procedure is the normalization. From the first graph, okay, sorry for that. From the first graph, we see the values of fundamental frequencies that span between 30 and 500 Hertz. That is normalized, and we get the second graph where the average value is 1. Here we have also the option of limiting some values, but in this case we don't need to do that. So from the second graph we see a presence of two distinct peaks, which actually occurs because male and female characteristic fundamental frequencies differ. So to achieve the third graph, we have to divide the values by the characteristic frequencies for male and female speech. So from the third graph, we can also already see different colors represent the values from different emotions. That some emotions already, the center of it is positioned slightly to the right or slightly to the left than the other. So usually the fundamental frequency is one of the best ways to distinguish between emotions. From for the experiments, we calculated features from window heights between 16 and 2048 milliseconds. But for the border cases of 16 and 2048 milliseconds, the recognition rates dropped. So because of that, we removed those processing window heights from further processing. From each processing window, 549 potential features were calculated. To remove the non-beneficial ones, we used the program package called VCAB, and provided us with a two-step approach. In the first step, we removed a lot of features already with the measuring of information gain. And for the second step, we were keeping the best subset of features to distinguish between classes that usually left us with a number of features between 25 and 50 features. Among the selected features, we saw patterns where some features were popping up more often. So these features was the fundamental frequency, then the male frequency capture coefficients, a low pass feature, which was a feature that we defined ourselves, free stimulus values, and the magnitude and energy coefficients. So the main focus of the paper was in selecting the best processing window wide. When choosing processing window wides, we are determining also the time frequency resolution. So with narrower windows, we get good time resolution, so this one, but bad frequency resolution. And with wider windows, we get good frequency resolution, but on the expense of getting a worse time resolution of parameters. So for the resolution of that one, we proposed a creation of multi-resolution window. This is done by having different processing window wides on top of each other. The first option is to have 3 windows centrally aligned with a different size. Which one? The problem here is that when we are shifting the window, we get to different overlaps. So for the widest window, we get the correct overlap. For the windows on the second level, there is no more overlap, and for the windows on the third level, we actually get empty spaces. So the information here is not processed, and which is certainly not desirable. That is why we designed a new window, where when this window is being shifted, there is no more left out information. Everything is being processed twice, which is nice, but the problem is here that at the start of the recording and at the end of the recording, we get some information that is not processed. So this is just like a small percentage, but anyway, we designed the third window, where even in the individual window, everything is processed. And we actually got, because of this full coverage of the basic window, we got the best results using a multi-resolution window that look like this. So with the extracting a feature in the single resolution approach, every feature generation is determined by the values of each feature window. To enable a direct performance comparison between the multi-resolution window and the single resolution approach, we needed to implement multi-resolution feature extraction in a comparable manner. In the multi-resolution window, the new window contains 7 different windows, which are calculated over various levels. That's why we get 7 times the values of features than in single resolution mode. So for the first step, we aim to reduce the amount of features on each level. This is done by calculating the average values for each level, and from then on, we just continue the same as in the single resolution approach. So firstly, by calculating the information gain parameter, and then by assessing subsets. For the comparison, we had the result from 6 different single resolution windows and 2 different multi-resolution windows. The single resolution approach is represented by this curve, and the multi-resolution results is represented by the columns here. So the best recognition rate was in the single resolution approach was here at 84.1%, which was actually topped by both the multi-resolution approaches with 85.5% and 87.6%. So those values were achieved by the multi-layer perceptron. To confirm the benefits of multi-resolution approach, we also tried to use other classifiers. So we tested a lot of them, but the best results were actually gathered with a random forest of these decision trees, k nearest neighbor algorithm, and also with Gaussian mixture models. So these were the best results for each of them, and we can see that the multi-resolution approach always gained higher recognition rates than the single resolution approach. The difference between them was 1.5% on average in absolute terms, which actually presents 8.7% of improvement in relative terms. Okay, so this was everything from my side. Have any questions?
Okay. Please feel free to ask.
I wanted to ask if you're considering various algorithms, do you think about constraints that will be from performance point of view of equipment that will run these algorithms? Meaning that you take a lot of windows, you process them, so I guess you increase demands upon the processor that will run this.
Yeah.
Do you somehow...
So basically in the learning phase, we had 549 parameters, which is not doable like in real-time processing. So even for the options that I explained here, those would not be really efficient if we would be calculating at once. But for this one, actually we can just once take the values and then calculate whatever feature we want. And for this one, we can actually take the same values and recalculate them again. And in the end, we are anyway calculating just like 20 to 25 features at once, not 500 or 1,500 as we do in the learning phase.
Okay, thank you. Are there any further questions? So maybe I will ask about some issues. You use overlapping windows. Yeah, maybe it could be faster to use just 3 steps of processing with windows with variable size. And the second question is, what is the shape of the window? Is it rectangular window or any other shape? Gaussian?
Let me see. So for the second question, we use the Hamming window.
Hamming. Yeah, okay. It's Hamming window.
I have it somewhere here for the others. We try different ones, so triangular, Hahn window, stuff like that. But this one actually provided the best frequency response. And for the first one, so we have to we have to load the values already, and when we have them, we can already just extract the features. So that's why we didn't do it like 3 times. This was all done in one go. And if we want to do in real time, then it has to be done at the same time.
But maybe another very small short question. What is inside VECA? What dimensionality reduction is inside?
VECA, this was actually developed by University of New Zealand. It stands for VECA 2 something. This is actually a really nice program package for machine with a lot of machine learning algorithms. We just have to prepare some known way of how the features are generated, and then we can try to use a lot of different subset evaluators. Some, let's say, we can use also a lot of this machine learning stuff like support vector machines or their multi-layer perceptron and like ADA boost, different trees. I don't know, there's really support for a huge amount of different classifiers. So we tried a lot of them, and the ones that I mentioned here, are the best.
Okay, so thank you once again. Well, starting from sound, we will go into ultrasound, because the third paper is entitled Assessment of Ultrasound Velocity Application for Chemical Process Monitoring. The presenter will be Mr. Dobilas Liaukonis from KTU, as I suppose.
Hello.
Yeah.
Hello, I am Dobilas Liaukonis from Kaunas University of Technology. I want to present presentation about assessment of ultrasound velocity application for chemical process monitoring. One of most popular material is epoxy resin, but this material without hardener have a poor properties. But after we mixing with hardener, we can get good properties solid material. This epoxy using for joining composites, composites manufacturing or coating and other purpose. But exists one problem. The sample or product in the mold, the product from mold need very fast remove. Need to minimize time for a curing. Need minimize curing time, and this time is have a influence of temperature or environmental other influences. Exist a few methods how can measuring the curing process, but all of the methods is a contact and measuring at surface of sample. The ultrasonic method is not contact. It measuring inside the product. The ultrasound velocity longitudinal wave is relative with mechanical properties, because in our experiments we measuring the velocity of ultrasound, and velocity calculating from thickness of sample and time of flight ratio. Setup is this, and with computer we modeling need signals and set high power supply voltages. With pulsar we generate these signals, divide excitation signals for precise excitation time measuring. Transmitted transducer convert electrical signals to ultrasound signals, and receive transducer take this ultrasound signals and convert to electrical impulse. Attenuator adjust the level of received signals, and acquisition system convert to discrete form. There is results of curing measurement in 50 hours, and we can demonstrate the three reasons of curing states. It's a liquid when hardener and an epoxy resin is mixed, gelation, and solid phase. If we take equal post-cured at elevated temperature speed to 100%, we can draw we can get degree of Q in percent scale, but there is some of variation because we trying see from where exist errors in measurements, and we have total errors. It's have two components, and calculating partial derivation get sensitivities for this and this component in our measuring system. Time of flight random errors we can define by Kramer-Rao law, and it's if we get more of energy in signals excitation or received, we can minimize these errors because we're using some of signals, and one of them is longer signals. The signals compressing with correlation in time domain. Where we're using discrete signals, we get a sampling frequency because the signals we interpolate with cosine interpolation. In this experiment, we're using three types of signals. There is a pulse which is short in time, have a flat bandwidth, but it's have a little energy. Next of signals is continuous wave burst, and the signals have more energy, but the frequency domain flatness is very little. And chirp spread spectrum signals, it's have more energy and flatness frequency range. And with the signals we get different random errors. We can see it's a biggest of errors we get with short impulse, and better situation is with longer signals which have more energy. And there is a velocity variation with confidence interval with 95% confidence interval, and we can set this system errors is neglected for all velocity variation. This variation can be from temperature variation in our laboratory in day and night time. One of problem. And in conclusion, the time of flight errors are influenced by the signal energy. Lowest errors are for Weidemann chirp, and velocity errors caused by time of flight and thickness estimation can be neglected in analyzed setup. It's a 0.1%. And future development need accounting for the error source, temperature variation and distance variation from transducers, acoustic contact variation, zero offset, nonlinear parameter study, or behavior with reinforcement, this epoxy. That's all. Can you talk?
So, please ask any questions. questions if you want. Yes.
I was wondering if you measure this epoxy material and at the beginning it's liquid, and when you put your sensor on this, so after it's hard you cannot remove your sensor. How's the real contact?
We using safety scotch on the transducer, but after coating the transducer, we use the zero time. What is the time if it's two transducer only two transducer without material of research, and
I believe the question is much more simple.
Yeah,
how you remove the transducers?
it's
Do
good.
you insert them into epoxy and stay buried?
no, we using a scotch, which is a I don't
No,
know.
the transducers probably at the surface of the mold. They are at the same level as the mold surface.
In this
Yes.
experiment, we using transducer directly contact with our epoxy. But in real measurements, we can use transducer on the mold where will product we're making a product, because the ultrasound can go from mold to sample and measure sample velocity, go to next transducer, or in the next setup we can measuring reflected.
Okay, so are there any further questions, please?
There is the last English in the vertical axis. What is the meaning of the vertical axis here?
There is
I missed the point.
this.
Yeah.
There is a percent of cured. How many percent is cured our sample? Because we measuring after 264 hours velocity in our sample. When it was heating, in the sample was heating, and we take this point. It's a 100%. This material is cured, and relating to this, we can say there is a 18% cured.
And once again, please, I missed the point, also the following point. What are the main conclusions of your research? What are your in two phrases, tell us the main conclusions of your research and main findings of your research presented here? I missed some points, perhaps I missed some points, so I would like to have the conclusion and the main results of your research.
We trying measuring the speed with different signals, and researching with which signals is minimal random errors.
And by the way, we have two kinds of errors. It's time of flight and errors, and what are
and thickness measurement.
So give us two parameters. Your error is.
We're using two parameters.
Two components.
Yes, two components.
Can you explain to us these two components of errors? I missed that.
One of values is thickness millimeter, and the next component is time, which time from measuring from two transducer. What time? How many time need ultrasound go from transmitter transducer to receiver transducer.
And final remark, you mentioned three kinds of pulse: regular pulse, chirp, and burst. So
We're using three types of signals. Is a short pulse.
All these three types, or you're using in this research all these three types, or not?
We're using three types of signals and two types narrow and flatness chirp.
What is the best choice between these three choices of pulses? What is the best choice for your
In our
research?
measurement, best choice is a chirp wideband chirp, and we can get little random errors. There's a chirp, the black line is from 0.5 to 5 megahertz.
Thank you very much. Better.
Okay. So thank you once again. Now
Excuse me.
we will. Okay. Now we will hear nice sound of money, as I suppose, because the paper is entitled "Acoustic Spectrum Analysis of Genuine and Counterfeit Euro Coins." Will be presented by Mr. or Mrs. Alina Gavrijaseva from Estonia. Please present your research.
So, good afternoon, ladies and gentlemen. And my name is Alina Gavrijaseva, and the topic of the paper I present here is acoustic spectrum analysis of genuine and counterfeit euro coins. The co-authors are Olev, Martens and Raul from Thomas Johann Sebeck Department of Electronics from Tallinn University of Technology. The agenda, here is presented the agenda of my presentation. The first part is introduction, then result of the FFT carried out on the authentic euro coins, then optimization of model analysis, results of fast Fourier transform based on the counterfeit euro coins, and in the end, conclusion. So here I presented the setup for analysis of the coin acoustic signal. It consists of the coin validation block with integrated microphone and oscilloscope. Coin under test is inserted to the shot, and then it drops again to the hard surface. And here is presented schematically the device, where number 1 is hard surface and number 2 is integrated microphone. Sampling rate of the oscilloscope is 1 megasample per second, and we store the signal with 500 milliseconds. So in order to reduce the size of data and minimize the influence of the noise and distortion, the signal is decimated 10 times. Here I presented the oscillogram and spectrogram of 2 euros, figure below, and here is original signal of the 1 euro and corresponding spectrogram of 1 euro. And here we could see that here are really natural frequencies that we need to discover. And in this figure, the result of fast Fourier transform-based analysis is presented. Here are the frequencies and corresponding relative magnitudes of all authentic euro coins. And as could be seen, the frequencies are really located in the separate places, what make it possible to separate and to recognize each coin. And each coin is presented in this picture in different color to simplify the comparison. Here is a numerical representation of the fast Fourier-based spectrum analysis, where only frequency at maximum and corresponding relative magnitude of each authentic euro coin is presented. And as could be noted, the sets of euro coins are really unique, that could it possible to separate coins. A novel approach for evaluation of acoustic signal vibration is applying of model analysis. Model analysis allows to measure and analyze the dynamic response during vibration. There are stability diagram and stability histogram in order to extract characteristic feature of signal in using model analysis. The number of modes or number of degree is an important input parameter of model analysis, and the greater is the number, the more expensive is more computationally expensive is the system. The number of degrees depends on the complexity of the structure of system. For simple system, it is in the range from 40 to 65, and in our experiments, the 15 was taken first. And here is presented the stability diagram of 2 euro coins. And next, the stability histogram is presented. In order to reduce the computational cost, several experiments with different input parameters have been carried out, and experimentally it was found that the 100 samples is enough for analyzing without reducing accuracy. And here in the stability histogram is shown the frequency distribution of calculated outputs, and the green line here is the decision level of the occurrences. It was also defined the experimental way, and as we could see, the most frequent, most stable frequencies here are 4, and we can see here blue dots on the places. So in order to optimize input parameters of model analysis, it was decided to reduce the number of degrees until the accuracy remains reasonable. So experimental way, it was achieved that number of degrees 20 is enough for good results. And the stability diagram, the result of 2 euro coin with optimized model analysis is presented, and figure below present the stability histogram of 2 euro coins with optimized parameter, the decision level of which is 7. And here we can compare the previous figure with 15 degrees of freedom and with 20 degrees of freedom. So the first here are more stable frequencies. The 3 frequency is enough for separating the coin. In this figure is in the first figure is a stability histogram of 2 euro coins, and the figure below presents the average of set of authentic 2 euro coins. And as we can see, the results are very similar, and the resolution is 15 Hz. So similar way experiments was carried out on the all authentic euro coins, and in this slide we can see the results with 2 euro coin, 1 euro coin, 15 cent, 20, 5, 2, and 10 cents and 1 cent. And as could be noted, the frequencies are located really in different places, so the natural frequencies are different for each euro coin. Here are numerical representation of this analysis calculated in Latvia. So here are presented the set of frequencies which is used for coin recognition. The next part of experiments was carried out on the counterfeit euro coins from Belgium, Italy and Germany. So here are three types of falsifications. The blue signal shows the original signal of the counterfeit coins, and here are corresponding spectrograms. So here is the result of fast Fourier transform-based experiments carried out on the counterfeit euro coin examples, and these pink lines are 2 euro coins just for comparison. So we can see that frequencies are really different for all euro coins, and they are different from the real 2 euro coin. The similar way model analysis has been applied to the counterfeit euro coins. The first figure shows the result of carried out on the counterfeit example of Belgian coin. The two stable frequencies was discovered in the spectrum of the acoustic signal. In Italian coin there was only one stable frequency, and in the last euro coin there is no stable frequency at all under such same conditions. So if we decide to make smaller this acquisition level, maybe we can find, but it is not interesting. So we need to discover it. And here is just for comparison the stability histogram of the original 2 euro coins. So we can compare all 4 graphs. And here are numerical representation. So the coin from Germany was out of range, so we couldn't define the stable frequency. And in conclusion, results of acoustic signal spectrum analysis for coin validation ensures authentic coin recognition detection of the counterfeit coins with high accuracy. Frequency response and model analysis methods provide unique set of acoustic parameters for each coin. And acoustic signal-based coin validation approach could be used as independent solution for coin validation and recognition. Here I would like to add that usually acoustic analysis was used only as a complement to some else methodics. So this method usually does not implement it separately. Thank you for your attention.
Thank you. Are there any questions about the money? Linas, please.
I'm wondering how you measure, could you open the conclusions? High accuracy. What is meant high and what is meant accuracy?
The resolution here was 15 Hertz, and I think it's not I think, but it is enough for validation of the coin. So we can not only recognize, classify, but we can also validate the coin using these results of experiments, and it is just by accuracy, I think.
Okay, I will put it in another way.
Okay.
How many coins were tested?
Do you mean
authentic coins and classification?
authentic coins? We have full box, different types. So a lot of experiments has been carried out, and we have 3 types of counterfeit euro coins. And last week we have also visit to Estonian forensic system, and we have some experiments there. So the parameters were pre-known, and we just tested our equipment, and results was that we was able to separate and to tell yes, this is.
Because that is my question. You have tested, let's say, 1,000 coins.
Not so much. Yeah.
Or something. So, in order to say that you have high accuracy, there are specific techniques and statistics which say that, I don't know whether accuracy is the right word, because accuracy is mostly used for measurements. Even though metrologists, they do not agree that we should use this word. But there is either detection rate and false alarm rate, or is a specificity and sensitivity. It depends.
My answer is the 100% of coins under test has been evaluated correctly.
And what percentage of the coins was from the counterfeit? Consider it as the authentic one.
Yes.
0?
From authentic ones?
No. How many falsificated coins were considered as authentic using the same parameter?
There was not such a result.
0.
Actually, no. In Forensic Institute, I asked about the coin with the highest quality. Mm-hmm. And there I had the result that it was separated, like it was, the result was, it is authentic. Mm-hmm. So yes, it is feedback, but it is a good result also. But we take this result in a team, and actually we heard the sound, and it was different from real one. So maybe this method needs more investigation.
Because I see that you have set thresholds arbitrarily, and setting the threshold in detection problem is the essential. You take the receiver operating curve and you take the threshold from the receiver operating curve in order to have the best separation. So that's not a question, most probably, but just an advice. Yeah. Thank you.
Thank you.
Okay, are there further questions, please?
I would like a question: is are these frequencies characteristics of coins, or characteristic of your equipment that was used to listen to the coin? Because if you design or assemble some other tube that you put the coin in, the frequencies could be different.
Actually, I think yes, because it depends on what equipment we are using for.
Yes, like this.
Yes.
The distance.
For data storing, it doesn't depend on the distance. It only we need the clear acoustic signal.
Well, maybe material of that surface that is hit by the coin is also.
But the point is that each coin has its own vibration. So if we start to design some new setup, for example, yes, maybe there will be some different frequencies, but they are different for each coin.
That means for other equipment you need to repeat your test and calibrate and find out these frequencies again.
Yeah, maybe it's just a study investigation.
Okay, but I would like to add the comment, because are you sure in your equipment do the coins fall always in the same way? Always
I
vertical?
try to do it.
Okay.
Yes, it influences, of course. Yes, so it is a point for another work. So we need to make such a box for acoustic system or acoustic signal storing that is more repeatable.
Okay.
So we need to design the trajectory.
Okay, but do you think, from your previous words, yeah, do you think some parameters of coins would change over time? After 2 years of using such coins, could be they different or not? Because you
mean parameters of
new coins. Yeah.
I had different coins in my experiments. So every coin has the year. Yeah.
Okay. Okay. Are there any further comments or questions, remarks?
Inflation does not affect the sound.
Yeah. Okay.
Just painted and the sound is the same.
So thank you once again. Now we have the fifth paper, a good example of cooperation between Lithuanian and Polish researchers. 5 Lithuanian authors and 1 from Poland, so the presenter will be from Lithuania, of course. Please present your paper about BoostEMD, an extension of EMD method and its application for denoising of EMG signals.
Good afternoon. My name is Mindaugas. I am a PhD student at Kaunas University of Technology, and today I'm going to make a presentation on BoostEMD, a method which was extended by us and its application to denoising of EMG signals. First of all, I would like to say a few words about EMG signals. EMG signal is physiological signal which is generated by human muscles, their movements, and it is applied in diagnostics of neuromuscular diseases, driver fatigue assessment, control of prosthetic devices, even interaction with computer software, for example, EMG-based spellers, and so on. So, first of all, I would like to explain the classical EMG method, how it works, and then I will explain our extension. So, EMD, or empiric mode decomposition, is a method which allows to decompose the complex signal into separate monocomponent signals, so-called intrinsic mode functions, and it is achieved by the following steps. First of all, we should identify the local minimas and maximas of the signal, and then perform the cubic spline interpolation between the maximas and minima, and then we get two curves, which is called in this case the envelopes. Then we have to calculate the mean of those two envelopes, and next we calculate the difference between the signal and the mean of the envelopes, and the remaining signal should fulfill some requirements, and the requirements are the signal should be equal to or differ from the number of zero crossings by 1, and the average of the remaining signal should be close to 0. And if those requirements are fulfilled, then we can state that the remaining signal is IMF, or instinct mode function. If not, then we have to repeat all steps that was mentioned before. And if we get the IMF, the first IMF, then we have to calculate the residue of the signal, which is calculated by subtracting the first IMF, and check whether it is above the threshold value, so some specific threshold value, and if it's so, then we can repeat previous steps with the residue and extract another IMF, so second IMF, third IMF, till the residue is below the threshold value. That means the composition is over, and that's it. So here you can see the graphical view of the EMD, and this is the in IMFs, or the monocomponent function of the signal, monocomponent functions of the signal. And we have decomposed this, for example, the signal in those monocomponent signals, and we can reconstruct the signal by adding all them together. But what we can do as well, we can simply discard some of the monocomponent function and so get rid of the noise. And it's usually we get rid of the first IMF, which contains the higher oscillation of the signal. And but still the critic for this method is that we cannot clearly know where is the how we separate the noise and the useful information. So when we discard some IMF, we lose some information as well. So what we suggest is that we should keep on extracting higher order IMFs from the first order IMFs. So our method, called BoostEMD, has 3 additional steps compared to the original EMD method. And of course, when we have the IMF and we would try to apply the original EMD method, we would get the same IMF, the same result. So first of all, we have to transform the signal, the first order IMF signal. And the first step of decomposing, of transforming, is that we should decompose each IMF into pair of positive and negative semi-defined functions, as you can see here. And then step 2 is that we should apply the upsampling operator by a factor of 2. Here is the upsampling operator indicated by this arrow to the top, and then we can apply the EMD method, and this process is called boosting, so that's why the method is called BoostEMD. And finally, the third step is the reconstruction of higher order IMF, and we can reconstruct it by downsampling each part, the negative one and the positive one, by a sample of by a factor of 2 as well, and add them together. So here you can see how the envelopes are obtained in the first order IMF signal. So we have first order IMF signal, and those lines over here on the top and the bottom of the signal is calculated by performing cubic spline interpolation, and those 2 curves are called envelopes. And this line, bolded line in the middle, nearly in the middle of the signal, is the mean of 2 envelopes. So now let's talk about the experiment we have carried out. We have used EMG physical action dataset from the machine learning repository. The dataset was generated by 4 subjects, 3 male, 1 female, age from 25 to 30 years. Each subject performed 10 normal and 10 aggressive activities. Normal activities were bowing, clapping, handshaking, hugging, jumping, and so on. Aggressive ones: elbowing, front kicking, hammering, headering, kneeing, pulling, punching, and so on. And we performed some classification. It was done under the assumption that the better the noising results, the better classification results. So the better method worked, the better classification results should be. And here's the results. You can see our method is here, we have discarded the second order IMF1 signal, and the classification results of original signal using support vector machine is here. The classical EMD, which usually discards the IMF1 results, is over here. So our results was better compared to those two methods, but still the best results of classification was using threshold IMFs, except maybe for clapping versus headering classification, which the best result was achieved by our method. And but furthermore, we have assessed our method by the noise by using some entropy and predictability metrics. This evaluation was done just for the noisy signal, and the predictability based on autoregressive model, which has two parameters like fit and random and root mean square error. So the error of noise signal should be as high as possible, and the fit should be as low as possible. And you can see that our method showed the best results for those two parameters, and the thresholding IMFs showed the best results in entropy parameter, but our method was not far away from this. And finally, we evaluate some statistic metrics like cross correlation and mutual information, and our method showed better results than classic EMD method, but still threshold IMFs show the best results, but our results are also close to it. Finally, some conclusions. The method we proposed does not have any parameter or basis functions. It is computationally not very expensive to improve performance. It is sufficient to modify the original EMD method so that only first IMF is extracted. The denoising results are superior as compared to traditional first IMF discarding method, both in terms of entropy and predictability of extracted noise signal, as well as classification accuracy using the noise data. However, the thresholding based method performs better for classification. The disadvantage of the method is that even higher order IMFs do not separate noise components from signal components clearly. Therefore, all noise cannot be extracted while retaining all useful information of the signal. And further research will focus on analysis of spectral and nonlinear properties of higher order IMFs and their practical application for important EMG domain tasks. Thank you for your attention. Maybe you have a question.
Yeah. So, are there any questions from the audience? We have time for one or two. Please, Linas.
I'm wondering what was the reason for selecting that particular technique for the data extraction? Because, for example, in the presentation by Alina, we saw that they used simple spectral analysis or even modal analysis.
Yeah.
And if you already know what pattern you should expect from the muscles or from neurons, I don't know what you actually register.
Yeah.
So maybe a simple correlation would have been better than trying to increase the noise. That's what I have understood.
The reason is that we don't actually know the pattern of where is the information that is useful and where is the noise. So we try to use some methods that don't require a pattern, so unsupervised methods.
Other questions? I have only a remark, because there are 6 co-authors of the paper, but only 4 subjects took part in the experiments. So
but it was a data set.
Yeah, okay.
It was not our generated data set. We
Okay.
took it from
So everything
data
is
set library.
clear now. Okay, thank you once again. And the last but not the least presenter comes from Opole Technical University in Poland. Alexandra Kawalajanik will present the paper related to another type of biomedical signals entitled Method of EEG Signals Pattern Recognition in Embedded Systems.
Yes,
Please present your results.
Okay, so thank you for a nice introduction. My name is Alexandra Kawalajanik, as Krzysztof said, from Opole University of Technology. I will show this very short presentation schedule, so short introduction to this study, short introduction to the BCI systems, because this is on what I'm working on, and some conducted research, future research plans, and summary. I'm not going to read it all, because I want us all to, not miss the bus for the trip. So, analysis of all biomedical signals is quite a very challenging task, and it's because, first of all, of the nature of these signals, and I'm going to show why they are very hard to analyze, and also because the EEG signals are generated with the human brain, it makes that them hard to analyze, because, as we probably all know, our brain has not been fully investigated yet by the researchers, and as probably in accordance with the literature study, EEG signals have become a very, very growing interest of numerous researchers all over the world, so that's why I got also some partners from various countries. And this is also because of seriously and constantly increasing development of brain-computer interaction related studies. Because in BCI systems, usually and mostly we apply EEG signals. This is because they are able, to give us information regarding brain's activity. And another key aspect of using EEG signals for the BCI systems is that the equipment is both inexpensive, quite, of course, inexpensive, depends what we understand under this term, and non-invasive. The BCI systems were initially developed in order to improve the communication with the external environment for handicapped users. Now we can use it also for gaming or other probably less important purposes. And the communication using EEG signals is both quick and easy, and as I said also before, non-invasive. And this is because these signals present our reaction to both real and imaginary motor activity. So as I said before, the analysis of biomedical signals is quite challenging. Why is it so? I'm sorry, I'm not so great with it. Obviously, we can divide signals into deterministic and random signals, and EEG signals become to the group of random non-stationary signals. Yes. So if someone is interested in the presentation, because I don't want to prolong it, I can send it or provide with it. As I said before, a very, very short introduction to BCI systems, because this is on what I'm working on. The rapid increase of many disorders in nowadays, such as stroke, ALS, or other spinal cord injuries, strongly affects our society, and it's about 2 million people in only the United States, so quite a large amount. And the result of it is growing interest in communication improvement, improvement of communication methods in order to provide both quick, efficient and non-invasive communication with external environment. As presented here, this is quite old now, sorry, but if we see how many papers are being published in regards of BCI systems, this is the interest is really constantly growing. And we can divide BCI systems into two main groups. First is non-invasive, and the second is invasive. Some researchers say that there is something like a semi-invasive method, but I would give it to the group of invasive systems because they require surgical intervention. And this very simplified general structure of the BCI. We've got the signals being composite, there is a feature extraction, classification, mapping, application. Sometimes we have a kind of stimulation of the subject. There is a presentation and the user gets the information it provides, and so on. If we want to make it simplified using emotive epoch headset, what I'm going to show you in a minute, we've got a user, this brain signals are being recorded, I analyze mu waves, I will say why. In a minute the signal is being processed, I have no filtering was done. The implemented action is the result. We've got some visual stimuli, not sound stimuli, because it also affected the quality of the signal when I did some initial study before. And as I said before, we have various BCI systems. Electroencephalography is non-invasive. There is no surgeon intervention, nobody is being cut, no blood, no nothing. And then we've got if we place some electrodes in the surface of the brain, we can say it's invasive or semi-invasive. I heard it does not help because probably brain does not generate any pain itself, I mean. And intracortical recordings very deep into brain tissue. It's quite, to be honest, invasive but efficient. This is how it looks like. I know some drastic. This is invasive. I'm not doing it. I'm a simple computer scientist. And here we've got a Mark Nagel. I'm going to tell a few words about him. This is a sample invasive electrodes just to give you a view how the brain activity can be recorded. And Matt Nagel is a guy who was stabbed with a knife, so he got his spinal cord injured. And then he was found because he was paralyzed by the cybernetics company, and they placed some invasive, very deep into tissue electrodes, which were able to replace and some of his motor functions. What was the result? Using only his thoughts, he was able to play a simple computer game, turn on the light, channels on television, to interact somehow with the external environment. It helped him quite nicely. So we've got, as I said before, recording methods. Why I'm telling constantly about this? If we look at the EEG electrode, the signal has to go through all those layers, including skull, bone, and scalp. And of course, the signal is quite weak. The wave frequencies are quite low, so as a result, is not the quality of the gain signal is usually not top. It's here presented again: scalp, soft tissue, skull, dura, cortex, and so on. Not a very nice thing. I used for my research purpose non-invasive brain-computer interaction. Here we've got a very professional EEG speller equipment from the company Intendix. It's about 20,000 euros if you want to buy it. This one is for $200 only, and it's a gaming headset which I have ordered from America a few years ago. And what we analyze here, I showed a short table with the very main brave waves, the frequency. I analyzed mu waves, and in accordance with some literature study, some researchers said mu brainwaves do not exist. This is a kind of significant variation of alpha waves, and some people say no, mu waves are separate waves. What's special about them? Because I agree that they exist. If we analyze brain, we've got all sorts of brain waves present, where mu waves only appear when the imagery motor action is being performed. So this is a sample. We've got some alpha rings, always artifacts, because what's challenging regarding analysis of biomedical signals, when it comes to the brain, we have both external and internal artifacts. External artifacts is like sounds, noisy environment, when something happens outside, and internal artifacts mean that our heart generates some artifacts. When we deconcentrate, that's what our body does, means that some internal artifacts may occur. And what's also, most of the current BCI solution often require expensive equipment. I don't mean expensive like fMRI, but a few thousand euros or dollars have to be spent. And simple, inexpensive, easy to buy headset, emotive epoch was for my BCI system implemented. And one of the main aims was to find, and of course to evaluate, EEG-based control techniques suitable for implementation in crowded, noisy environment. Why so? One of my colleagues is impaired, he had an accident, he can't move, so we were thinking about making a system which would enable him to move on his wheelchair, and we decided we can't do the test in a laboratory, quite nice environment, because then if you would go with the system on the street, it would probably not work, he would be killed or overridden by car. So I did many of the tests in crowded noise environments, like in similar to real life conditions. And as I said before, we've got various EEG-based BCI systems available on the market. Some of them contain really large amount of electrodes, like up to 256. But the complexity does not always go in hand with the proposed system's efficiency. In my point of view, sometimes less means more. So I'd used only 2 electrodes from the Emotive Epoch headset, and I wanted to implement it on an embedded platform, which of course caused some limitations. Okay, did I do? No, in here. So this is Emotive Epoch headset. Why did I choose it? First of all, it's non-invasive. Secondly, it's quite inexpensive, around $200, up to $500 with better developers SDK. It's portable. It consists of 14 saline and 2 reference electrodes. They are placed in accordance with the 1020 system. The data is transferred via Bluetooth to the computer. The sampling rate is not too great. It's quite poor, 128 Hz, but it was fair enough. It worked for gaming, so it could work also for me. And this is one of my subjects, my supervisor, but he was very great for testing. He had no hair, almost no hair on his scalp. Perfect. So what's important? Only signals with limited information were investigated. I did not have professional medical equipment, and the signals were generated during the process of imagery hand movements. The system presented in this paper was based on analysis of the mu waves, as I said, which oscillate between 8 and 13 or 12 Hz, so it's quite low. And they, of course, as I said before, they reflect the response to the execution of actions. And as I said before, it's possible to find them in imagery motor actions. The research was carried out in a real-life conditions, as I said before, and simple visual simulating application was applied. The electrodes were placed in F3 and F4 positions. We've got here, just for you to compare, a 1020 electrodes placement system. So Emotive meets the standards. The embedded platform I used that time because the study is not very new, and because of financial reasons I had TS7260. Now I would rather use Raspberry Pi as an embedded platform because it's a bit more powerful, and it wasn't a real standalone application, but it worked somehow. I used some MATLAB and so on. What's not going? And what's important, the system is going to be both portable and implantable on embedded platform. We cannot use sophisticated signal processing methods which require high computing power. We need to meet the limits. The embedded platform usually is quite small and require possibly the least resources, and processing power should be considered. It's quite important. And because of that, we cannot use popular artificial intelligence-based methods or evolutionary algorithms. Or some people ask me, why don't you use many statistical things? And I said, I can't, because if I chose my limits in embedded platforms, I have to stick to simple but efficient methods. So if you look in here, this is my method. It looks quite nice. It took me some years to make it. We've got here the analysis in time frequency and domain, and here is in the frequency domain. Here you can set up which is more important, and then I will explain you. If we look to the equation, the method has a bridging property, and it means that lesser sensitivity to disturbances affects the compared signals, and by the normalized, so it means related to maximum values of signal and pattern values in time and in frequency domain were denoted. What's important? We had, you saw these two coefficients, A and B, and these are using as weighting coefficients. And what does it mean? We can use them ultimately to decide which proportion the time and the frequency components of signals and patterns should be considered during the analysis. For example, if I set the value A to 0.5, both time and frequency components would be considered equally. While setting, for example, A to 10, said that we would exclude the frequency component, we probably would not gather the data in that domain. So this is how it looks. Where this is the simulation application. So for example, someone had to relax from first to 10th second, then imagine to move right hand, left hand. It was up to you. I did it here like this, but you could, the potential user could set up, we could set up experiment in the way we really wanted. And the efficiency of the pattern recognition method was quite high, around 84.7%. However, only 15 healthy. I was allowed that time only to test healthy adult subjects to test. Now I got some, how do we call it, ethics committee agreed for me to perform further tests in hospitals, but it was like more pilot study. False positive and false negative results in this are a big issue in pattern recognition process and almost all biomedical signals. If we've got here false positive. We've got sample 1. Here is a left hand recording the F4 electrode, and we have right hand in 3 electrode movements, imagery movements, of course. Of course, they oscillate around similar values, but in this case, they were found as being the same signals. This is quite a big issue while analyzing EEG signals. In this case, we have both right hand imagery movements. The absolute value was 0.8. The signal matched. Everything was fine. Not to prolong it, the proposed method of signal pattern recognition may prove its usability, in particular on embedded platforms implementation. And it's something that these systems are currently more powerful than it was in the past, and it's developing and everything. It's getting small, like mouse box, and everybody wants to have small computers. So the accuracy, as I said, was relatively high. And it was based on only addition, subtraction, multiplication, division. The method can be applied in any programming language, almost on any system. And of course, as every work, it raised some challenges and questions about the efficiency while using cheap EEG amplifiers, such as emotive epoch headset or Moose, or I did some also tests on OCZ, but it did not work. And as I said before, using basic mathematical operations for the signal processing purposes is quite a novel approach. I have not found anything similar in literature, but especially in area where complex sophisticated signal processing methods could not be applied. And of course, signals were very noisy and sensitive. And what are my further research plans? I want to implement other biomedical signals or data. I got some contacts with a hospital where fMRI is being used, so I could do something with it. And I'm now learning and implementing a non-integer calculus-based methods also for analysis of EEG and EMG signals recently. So this is the system we're building now, emotive with some EMG and so on. And thank you very much for your attention. I'm sorry that I spoke so quickly, but I did not want to prolong. And in case you have any questions, you can ask me now, or ask me later, or email me anytime.
Thank you very much. Saved a lot of time, but we have the time for discussion now. Are there any questions?
Yes, how did you calculate the frequency parameters? It's just Fourier transform?
I didn't do filter. I just, how was it? In MATLAB application, I cut the frequencies. It wasn't typical filtering, but on my application, it's only analyzed from between 8 and 12 hertz. So, in order to catch the mu waves, I know similar to mu waves, and so that if the subject had to think every, like, let me say, we could measure in the signal because we had this simulated application setup. So I knew that after, like, for example, 5 seconds, he was supposed to think about moving right or left hand. So that's why it was also easier to catch compared. And I did not have a database of signals. We compared each signal with each signal. It was a bit crazy, but we did not have a database. We built up one, and the signal was both pattern and signal. So it was like that.
Thanks, Alina. Further questions or remarks?
Yes.
I was just wondering if you apply such systems on animals, their brain activities are more simple than humans, or?
To be honest, I'm a computer engineer, and well, I don't know if someone would give me an animal for testing, but it's quite nice hint. To be honest, I saw some open source data coming from rats, I think. I'm not so sure. Well, some people test their movements, but I concentrated myself that time on healthy adults, human beings.
Okay. Any other remarks? I would say it's good to have such supervisor who trusts you, but he knows that it's non-invasive, because if it would be invasive, I wouldn't trust any young student, for example. Okay, so if there are no questions, thank you once again.
Thank you.
As this was the last presentation today, we have 45 minutes of resting before the bus departs. Thank you.